We're going to do some AP free response videos today. Right now I'm doing 2010 AB free response 3. It is an AB only question. It was not on the BC exam. All right, so I drew a terrible version of the graph, so hopefully you have the 2010 question 3 AB free response in front of you, but we'll walk through the question. So there's a fairly long intro, which I think a lot of us find daunting, but not all of the information is relevant, and certainly it just looks extra long, but it's not awful. So there are 700 people in line for a popular amusement park ride when the ride begins operation in the morning. Once it begins operation, the ride accepts passengers until the park closes 8 hours later. While there is a line, people move on to the ride at a rate of 800 people per hour. The graph here shows the rate R of t at which people arrive at the ride throughout the day. Time t is measured in hours from the time the ride begins, which is t equals 0, till the time the ride closes, which is t equals 8. So part A, how many people arrive in the ride between t equals 0 and t equals 3? So an important piece of information to get here is that this graph, R of t, right? So R of t is the rate people join the line. Oh, if you hear screaming in the background, it's my tiny 2-year-old son who's running around downstairs with his other mama. It's not a big deal. But anyway, that's why if you hear random child screaming, it is and dog barking, in case you heard that too. There's dog barking too. Utter chaos here at the Hogan household. It's all good. Quarantine is super fun. All right. So anyway, R of t is the rate at which people join the line, right, in people per hour. So I want to oversimplify this for a sec and talk about the fact that the AP really likes this kind of problem that involves a rate in and a rate out. So in this problem, it's the rate people join the line, rate in, and then the rate people process through the line to get on the ride, which is the 800 people per hour. That's a rate out. There's a rate in and there's a rate out. Sometimes on an AP problem, it's people getting on an escalator. Sometimes it's snow falling and someone shoveling the snow. Sometimes it's people putting fruit on a fruit stand and people buying the fruit. There's a rate in and a rate out. Sometimes it's pouring something into a container, but the container has holes, so there's an amount leaking out. Rate in is how fast you're pouring it into the container. Rate out is how it's leaking out. These rate in, rate out problems are a really broad category of problem that comes up a lot on the AP and has for like the last, let's say, 10 to 15 years, right? So since the mid-2000s, at the very least, these rate in, rate out problems have been pretty common. So knowing how to do this one is just one subset of knowing how to do all of the rate in, rate out problems. So anyway, this is a rate in, rate out problem. So this is the rate that people are getting in line, and what they ask for in A is how many people arrive in the line. So if you have a rate, right, if you have a rate, which is like a rate of change, if you want to find the quantity, you do that by integrating, right? So if we want to know how many people have gotten in the line, so our part A is going to be the integral from 0 to 3 of my R of t dt, right? So I want to integrate the rate, right? And that's going to give the number of people that have gotten in the line since the beginning, right? If I integrate the rate, it'll give me the number of people. So the thing is that is this shape right here, right? Which is a simple geometric shape. Now, admittedly, my graph is really crappy, right? My graph is really crappy, but there are essentially two trapezoids here. There's the one from 0 to 2, right, that you can find, and then there's this one. And that's not a trapezoidal approximation. They are actual trapezoids, right? So if I do the first one, right, the first one has a base of 2, right? Well, I'm sorry, a height of 2 along this base, right? And then the two bases are these two parallel sides. So it would be 1/2 the height of 2 times the sum of the two bases. Well, the one base on the graph, and I'm going to look at the real graph, not my graph, because my graph is bad, is 1,000. This is a 1,000 on the real graph, and this is a 1,200 on the real graph, right? And then the second trapezoid has a height, like this width down here is a 1. That's the height of the trapezoid. So 1/2 of 1 times the sum of the two bases, and this base is again the same 1,200, and this is an 800. So again, I did use trapezoids to find the area, but it's not a trapezoidal approximation. It's the actual area because this graph actually has trapezoids as its shapes. When you clean this up, you get that it is 3,200 people. Okay, so there were 3,200 people that joined the line in the first 3 hours, right? Second, and they do say show the computation that leads to your answer, so even if you can do this geometry in your head, please don't. Please show your work. Next bit. Is the number of people waiting in line to get on the ride increasing or decreasing from t is 2 to t is 3? Justify your answer. So this is where that rate in, rate out stuff is related. So I'm going to call L of t. So in my own notation, I'm going to call L of t the number of people in line. Okay, so it's not a rate, it's the number of people in line, right? Another way to think of that logically is it's the length of the line, right? So like if 100 people were in line, we'd call L of t 100. Okay, so L prime of t, which is the rate of change of the line length, right? Rate of change of the line length, right? Well, that should be the rate in minus the rate out, meaning it should be the rate that people are getting in line minus the rate that people are leaving line, right? Because the rate in is the people joining the line, R of t, and the rate out is a constant 800, right? Like every hour, 800 people get pulled out of line to get onto the ride. So essentially, this is one way to think about this logically, and this is going to come in handy a lot more when we get to part C. But if you're thinking about it this way, that the net rate of change, which I happen to call L prime of t, is rate in minus rate out. And that's going to be true whether it's the snow falling minus how fast someone is shoveling, or the people getting on an escalator minus how fast they're leaving the escalator, the fruits that you're stocking on a shelf minus how fast people are buying the fruits, the water that you're pouring into a bucket minus the rate at which the water is pouring out of the bucket, right? Rate in minus rate out. And that's going to be true in all of these problems. So the short answer here is that if R of t, so what I want you to notice here is that if R of t is bigger than 800, the line is getting longer. Because if R of t is more than 800 people, that means that more than 800 people joined the line, but only 800 people left the line. So the net rate of change, right, the rate of change overall for the line is positive, meaning the line is getting longer. But if R of t is less than 800, then the line is getting shorter because more people are leaving the line than joining the line. So the reason that's relevant, I'm going to go back up to my really terrible graph, and I did go out of my way to label 800 on here, is that in the window from 2 to 3, if you notice, R of t, right, so here's 2 to 3, R of t is up here, and 800 is down here, meaning that R of t is bigger than 800. So since on the window from 2 to 3, R of t is bigger than 800, the line's getting longer, right? So line is getting longer, but if we put it in the way they worded it, right, because you should always try to use what they said, the wording they said was, is the number of people in line increasing or decreasing? Well, that's the same thing as saying the number of people is increasing. So number of people in line is increasing, right? Okay, so that's my part B, okay? Next bit, part C, I need to erase some stuff if I can figure out where I put the lovely eraser. There we go. All right, so I'm going to keep my terrible graph because it might come in handy again. All right. Okay, so part C. At what time t is the line the line for the ride the longest, and how many people are in line at that time? Okay, so for part C, here's the thing. They ask, when is the line the longest, right? So we already said that L prime of t, right, was R of t minus 800, right? Like this is the rate of change. And what they're actually asking you for in part C is they want when L of t has a max. Now, I made up this L of t notation because in my brain that was an easier way to think about it. So L prime of t is only a notation that I made up. It's not in the AP. But the point I'm making here is that if I want to know when the line has a max, I want to know when that line's rate of change is 0. That's what we call critical points, right? That's how we find extrema. So critical points are either when the derivative of a function is 0, right? Which in this case would be when R of t is 800, right? And we're going to talk about why that's significant in every rate in and rate out problem. Or when L prime of t doesn't exist, which is not going to be an issue in this problem because this is a real world application. There is no does not exist situation. Or at an endpoint, right? So the line could be the longest at the start of the day or at the end of the day, right? And neither of those is likely. Like even if you just think logistically, the line is probably not longest right when the park opens, and it's probably not longest at the end of the day when most people have gone home. So chances are that the critical point I'm going to want is when R of t equals 800. Now, by visual inspection, which is just a fancy way to say you used your eyeballs, using your eyeballs, you can see that R of t is 800 at only one spot on the graph, and that's at t equals 3, because they gave you a better graph than what I have. So you get a critical point at t equals 3, and then technically you have the two endpoints. If you feel the need to make a sign chart, you can. So I'm going to make a sign chart to show you, but you can also use logic to figure this out. So one way to notice this is that, remember, we discussed in part B that if R of t is on top of the 800, then that means the line is getting longer, right? line gets longer because the rate in is a larger y value than the rate out, right? But if the rate out is bigger than the rate in, then that means on this window, the line gets shorter, right? Line gets shorter. So essentially, the short answer here is the line is getting longer in this whole window, and then it starts getting shorter, so the longest it gets must be that moment when it turns around at t equals 3. If you need to make a sign chart to show that, you can, right? You could say, oh, the rate of change is r of t minus 800, right? From 0 to 3 to 8, right? So we know that the net change is 0 at 3, right? Like r of t is 800. But we can see because r of t minus 800 would be positive in here, and then r of t minus 800 would come out negative when r of t is lower, that what's happening is my line, which I called L of t, but if we just want to be clear, is increasing and then decreasing, meaning that the max happens at t equals 3. So this is the max. These are both mins, right? So the second question in this sub-question, right, in C, the second sub-question is, how long is the ride at that time, right? So what we need is we need to know what the line value is. So we need the number of people at t equals 3, right? Well, if I want the number of people at t equals 3, right, really what this boils down to is how many people started in the line at the beginning plus how many people did we gain in the window from 0 to 3, right? And minus how many people left the line in the window from 0 to 3, right? That's really what this is going to be. How many people were standing in the line the moment the park opened? Well, that's 700, right? Plus, I gained the number that I actually had in part A, this blue area that I found. I gained the integral from 0 to 3 of r of t dt, which was totally my part A, right? And I lost 800 times the 3 hours because I lost 800 people each hour, right? So what's going to end up happening is I end up getting a 700 plus the 3200 that was my part A answer minus a 2400 for a net value of 1500 people in line. So the longest this line ever gets is 1,500 people, which is a pretty epic ride, I would hope, because that's a lot of people. Okay, so part D is going to relate to C. So what I'm going to do is I'm going to erase above here, but I'm going to keep the bottom part of part C because it's relevant, okay? So when I go to do part D rather, right? This was my answer to part C. Part C says, write but do not solve an equation involving an integral of r whose solution gives the earliest time t at which there is no longer a ride. So see how this was what I called, like, using my own notation, this was L of 3, right? Like this was L of 3. It was the start value, 700, plus the integral from 0 to this 3 that I picked, minus 800 times this 3 that I picked, right? Okay, so it's that same logic when we go to do part D, except instead of this being a 3, I really want this to be a t, which means I want these guys to be t also. Now, there is one little limiting factor for that. So the number of people in line, right, the number of people in line at t, right, so at time t, which I'm going to call L of t, right, that's my own Hogan notation, is going to be the number of people that started in line, which is still 700, plus the number of people we gained in line. Well, that's going to be the integral from 0 to t now, because I'm not integrating to 3. I'm integrating to some mystery time. But here's a little caveat about this. I can't use r of t dt. If t is one of your bounds, you have to pick a different letter to use for your variable of integration, right? Because this is a bound. So the AP used s. I use x. It doesn't matter. You can pick any variable that is not otherwise used in the problem, right? So the integral of r of x dx, right? So this was the number I had at the start, just like we saw in part C. This was the amount that I gained, right? I gained that many people in line from 0 to t, minus the number that I lose, right? Which is the 800t. And if I want to be more consistent in my tenses, this would be lost because I used a past tense for gained, right? So my answer for this is going to end up being 700 plus the integral from 0 to t of r of a variable that is not t, d that variable. So I picked x, the AP used r of s ds, I used r of x dx, you could use r of y dy, it doesn't really matter as long as you're picking a variable that is unrelated to this problem, and then minus 800 times t, because again I want, if it was t hours, I lost 800 per hour. So that's my part D.